Welcome to the next class of Data Communication Network. So, we were discussing unit number 3, network layer. In the previous sessions, we tried to understand what is a network layer, a brief introduction about network layer, then one of the important functions of network layer called forwarding and routing, and the differences between the forwarding function and routing function. Then we tried to understand what do we mean by network service models. Here we have different types of services expected by network layer, and based on those services we categorized to two types. The best effort service will be referred as internet, where you try to deliver the packets but you cannot provide any guarantee. And the second kind of service where you can expect some guarantee within the expected delay and in the order delay, which we refer with asynchronous transfer mode. We have different versions of asynchronous transfer mode, namely variable bitrate, constant bitrate, available bitrates. Then we started discussing of categorizing the networks based on the type of service provided by network layer. Here, if the network layer is trying to provide a connection oriented service, we refer with the name called virtual circuit networks, and if it is providing a connectionless service, we refer it with a name called datagram networks. We try to understand the functionality of these two types of networks, and also we try to understand the origins as well as the comparison between the two types of networks. Then we started discussing on. In the previous class, we discussed about one of the important components of a network layer which plays a crucial role in routing called as router. So, what are the internal components of router which helps it in performing the function called routing? What are that? Input port from which it receives the data, then the switching fabric from which it determines the forwarding process and try to forward to the appropriate output port, the output port through which it is connected to the end device or to the next router, and to implement the routing function we use one more component called routing processor. In today's class we will be trying to understand two mechanisms happening in router called queuing mechanism and routing control plane. Let's discuss the first topic of today, queuing mechanism. So packet queues may be forming at both input ports as well as output ports. We have just discussed in our previous class the structure of router. So the input ports are through which the packets enter into a router, and output ports are ones through which the packets will be released to the next router or the destination device. So the queuing of this packet can happen either at the input port or output port. The location and extent of queuing will be depend on traffic load, the relative speed of switching fabric, and the line speed. So here the traffic load is total number of datagrams that have been or packets generated. The relative speed of switching fabric is the speed at which the switch will move the packets from input port to output port, and the line speed refers to the speed at which datagrams are generated by the input ports or are transmitted out by the output ports. Input and output line speeds, that is the transmission rates of these two line speeds, we are assuming that they have an identical transmission rate, and that is equal to R line packets per second. So the input and output ports transmission rate, we are assuming it as R line per packets per second, and the number of input ports and output ports are n. Now the switching fabric, the one which is actually forwarding the datagrams from input to output port, the switching fabric will be transferring the datagrams at a rate of R switch as the rate at which the packets can be moved from input port to output port. So what are the things we are assuming? Input and output ports are total in number is n, and their switching speed, line speed is R line, and the switching fabric speed which is used is R switch. Now when for an n input and n output port, the R switch is assumed to be n times faster than R line. If R line is equal to 1 and number of input ports are 3, then our switch is 3 into 1. Okay, so when we have such a high switching fabric speed, then only negligible queuing will occur at the input ports. Simple. Whatever the packets that come at the input ports will be accepted by the switching fabric, so you don't find any kind of queuing that may happen at input port. This is because even in the worst case, all the input lines, if I have n input ports, all of them are having datagrams, still they can be managed by the switching fabric because its switching rate is n times the line speed of the input port. So all the packets can be accepted by the switching port. Since the but what we are assuming, the line speed of input port and output port is R line. And here we are getting some packets at the rate of n into R line. So definitely what happens, the output port can transmit only single packet in a unit time. Just like one input port, one packet can be transmitted, the one output port can transmit only one packet at a time. But all the packets from this switching fabric, if they are targeted to the same output port, what happens? In n number of packets, one will be transmitted and remaining n minus 1 will be have to be wait, and this need to be completed before this particular output port is become free. So this is how queuing will be happening in general mechanism, and we are particularly here talking about queuing that may happen at output port when the switching fabric speed R switch is n times the line speed of the input port. In the previous slide, we were talking about happening of queuing mechanism either at the input port or output port. First, let us start discussing about input port queuing. In input port queuing, for instance, the switching fabric which forwards the datagrams from input port to output port. And here the R switch, that is the rate of switching fabric, is slower than the input ports combined. In our previous slide we assume that there are n number of input ports with a speed of R line. So n into R line is greater than the R switching. So what happens when the number of datagrams at the input queue will definitely increase, and this results in the queuing mechanism occurring at the input ports. What happens when queuing mechanisms develops at input ports is it results into a queuing delay because all datagrams or all packets cannot be transmitted at a time, and this will result in a loss due to input buffer overflow. Definitely there may be some scenario where the packets will be lost because of the input capacity overflow. Here we have a mechanism called head of the line blocking. What do you mean by head of the line blocking is the queue datagram at front of the queue prevents others in the queue from moving forward. For instance, here we have two datagrams. So the first datagram is trying to prevent the second datagram to move forward. That is what we are referring with head of line blocking. Okay, let us look at the first scenario. Here at time t, you find the three input ports. Each of it is having one datagram to be transmitted. The one input port 1 and input port 3 are planning to send to the output port 1, and the input port 2 is planning to send the data to output port 2. Okay, so for case of 2 we don't have a problem because there is only one input port which is trying to send the packet or datagram to the output port 2. But here for output port 1 we have both input port 1 and input port 3 trying to transmit, but only one datagram will be taken at a time. So what happens here? When one datagram which is at the top, the one which is indicated in the red color, is transmitted, the third input port's datagram, the one with the lower red packet, has been blocked because it can be sent only after the datagram of one has been transmitted. But this particular blocking of the datagram from one of the input ports because of the other input port which is existing before it in the queue, that is called as head of line blocking. This is one scenario. The output port contention, only one red datagram can be transferred and lower red packet is blocked until the first datagram is transmitted. Now look at the second scenario. Here what is happening is it's one packet time at input port 1 is trying to send a packet to output port 2, and input port 3 have two datagrams, the one in the red color and the other in the green, and both of them have to be transmitted to output port 1. But what is happening is in the queue the red datagram is first, so until the red datagram is transferred to the output port 1, the second datagram which is in green color cannot be transmitted. What is happening here? The green datagram which is in the green color has been blocked by the red color datagram in the input port 3. So this is also an example of head of line blocking. In the scenarios you could observe the input port 1 datagram is blocking input port 3 datagram, or the input port 3 two datagrams, the first datagram is blocking the second datagram. So here queuing mechanism is happening at input port, so that is why we refer this as input port queuing. In the previous slide we were talking about queuing mechanism that may happen at the input port end. Now let us look at the queuing mechanism that can happen at output port queuing. For input port queuing, one of the condition required is the switching fabrication speed must be less than the n number of input ports into their line speed. So something like R switch is less than n into RL. But for output port queuing, what we assume is R switch is equal to n into R line speed of input ports. Why I am making this particular assumption is, at a time t, a packet has arrived at each of the incoming input ports. So we have three incoming input ports, 1, 2 and 3, and all these input ports have datagrams or packets to be transmitted. Now what is the speed of them? We assume this is R line, which is equal to each of them is transmitting one datagram at a time, so its speed is 1 packet. Now all these three input ports would like to transmit through the switching fabric. Now when can switching fabric can accept all the three datagrams from the three input ports? When its switching rate is n times the R line speed. R line equal to 1 and here capital N equal to 3, because we have three input ports. So here the switching fabric speed R switch is assumed to be 3 into R line, which is 3 into 1. So it will accept all the three datagrams which are transmitted by the three input ports. Once all those three datagrams are collected by the switching fabric here, but what is the thing that we are assuming is all the three packets have been transmitted over the switching fabric to the same outgoing port. So we want to transmit all the three input ports would like to transmit the datagram to the output port 1. So what happens is switching fabric collects all those three datagrams and will be transmitting to the output port 1. So output port 1 has received the three datagrams that have been transmitted in the previous time period. But what is the capability of your output port? Same as input port, that is only one packet at a time. So what happens here is, out of the three datagrams received by output port, only one packet will be forwarded to the next, and remaining two datagrams will be in the queue. The next time we will be sending the second datagram, and in third time we will try to send the last datagram. So till that time the two datagrams will be in the queue till the first datagram has been sent out of the output port. So what is happening in this scenario is the switching fabric speed is almost equal to the n times of the input port speed. So it can accept all the packets at a time and can transmit to the one common port at a time. But the output port doesn't have that much speed, so they need to transmit only at their capability of one datagram per unit time, and remaining datagrams will be left in the queue of the output port. That is what we refer it as output port queuing. So in the example, out of the three ports, only one packet has been transmitted, the two new packet, then the remaining two will be in the queue. Now next scenario what we could find is, this is a time 1. Next time you find two more packets, one from the input port 1 and second one is for input port 3, and input port 3 is again trying to transmit it to output port 1. So here already two packets are in the queue, so this may add and now it becomes 3, because one of those 3 packets will be transmitted out, and again it is adding to the queuing at output port 1. So this is what output port queuing is, and this is how the queuing mechanism is implemented in input port and output port. Whenever a queuing mechanism is generated either at the input port or output port, we need certain buffers to store those datagrams. So router buffers are needed to observe the fluctuations in the traffic load. What is the fluctuation? The capability is only one datagram per unit time, and you found 3 datagrams at a time. So to hold those 2 extra datagrams, we need buffers. So the rule of thumb is referred as RFC, ready for comment 3439 rule of thumb, indicates average buffering required is equal to typical round trip time times the link capacity. The link capacity of the transmission is C, then the average buffering equal to product of round trip time. We discussed previously what is round trip time. That is the time taken from one end to other and to come back to the same point. So that is called round trip time. Generally it is 250 milliseconds, and that has to be multiplied with the capacity to find out the average buffering which is required. So for example, if capacity of the link is 10 Gbps and the round trip time is 250 milliseconds, the average buffering required is product of C into RTT, which is nothing but 10 Gbps into 250 milliseconds, which will give us 2.5 gigabit of buffer is required. A recent recommendation is, with n number of input flows, the buffering is equal to C into round trip time, which we have discussed, has to be divided by square root of capital N, and indicates the number of input ports or output ports. The next topic which we would like to discuss is routing control plane. When we discussed the router's architecture, we discussed that a router has 4 important components: input port, switching fabric, output port, which are together will be dealing with the data plane, and the 4th component called routing processor, which will be associated with routing control plane. In our previous discussion, that is while we discussing the router architecture, we made an assumption that routing control plane fully resides and executes inside a routing processor within the router. So our entire routing control plane will be implemented within the router inside a component called routing processor. The network wide routing control plane is decentralized. If I have 10 routers, every router will have its own routing control plane, and it is a decentralized version, and these routers will be communicating with each other. So routing control planes of each router will have to send some control exchange messages with each other to implement the routing function, because the routing control plane is executed independently by each router. Now additionally, the router and the switcher vendors bundle their hardware data plane and software control plane. The switching fabrics, which will be taking care of this hardware data plane, and routing processor, which takes care of the control plane, they need to be integrated together inside the router. But nowadays researchers has made a new change, or the change in the existing architecture. What they believe is a new router control plane architectures in which a part of control plane is only implemented in the routers, that is local measurement, reporting of link state, or forwarding the table installation and maintenance. These are the few functions which are a part of routing control plane will be implemented inside the router along with the data plane, which is taken care by the switching fabric and input and output ports, and a part of control plane can be implemented externally to a router. So not completely the execution of the control plane will be done inside the router, only a part of it will be done inside it, and the remaining part will be done externally to the router in a centralized server. Means for all the 10 routers we are assuming that will be done in centralized server, which could perform the route calculation. So If control plane function is calculated as something like 100%, some portion like 40 or 50% will be done inside the router and remaining has to be done in the centralized server, and that will be common to all the routers which are being part of that routing path. So a well-defined API indicates how these two parts, what are the two parts? The control plane implemented in the router and the control plane that is implemented in the centralized server. They will be trying to interact and communicate with each other, and this will be separating the software control plane from hardware data plane. Hardware data plane taken care by remaining three components, and software control plane taken care by routing processor. And it can simplify the routing by replacing distributed routing calculation with centralized routing calculation. An innovation by allowing different customized control planes to operate over fast hardware. The reason why we are adapting for this change is we want to improve the routing speed and improve the performance of the routing. So this is what we have for routing control plane. So we discussed two important topics: queuing mechanism and routing control plane in this session. The internet protocol is our next topic, which we'll try to discuss in the next class. Thank you.